Hello dear students. In this lecture we will discuss about the time frequency analysis. Mainly we will see how we can apply wavelets to biomedical signals. Mainly we will consider here the EEG signals. So a transform can be thought of as a remapping of a signal that provides more information than the original signal. The Fourier transform fits this definition quite well because the frequency information it provides often leads to new insights about the original signal. However, the inability of the Fourier transform to describe both the time and frequency characteristics of the waveform led to a number of different approaches as we have described that in the last lecture. So the wavelet transform can be used as another way to describe the properties of a waveform that changes over time, but in this case, the waveform is divided not into the sections of time, but we can say the segments of scale. Now the expression for the continuous wavelet transform can be derived, and we can say that in the wavelength analysis a variety of different probing functions may be used, but the family always consists of enlarged or compressed versions of the basic function as well as the translations. So you can see this equation number 1, that is W is for wavelet AB, these are the parameters, integration running from minus infinity to plus infinity xt 1 by square root of mod A. Then you see this phi function, basically this is a, we call it as a mother wavelet conjugate. It is dependent upon basically t's, that is shifted and scaled. So this integration with respect to again time. Now here B acts to translate the function across xt just as t does in the equations, and the variable A acts to vary the time scale of the probing function phi. Now if A is greater than 1, then the wavelet function phi is stretched along the time axis, and if it is less than 1 but positive, it will contract that function. And the negative values of A simply flip the probing function on the time axis. While the probing function phi could be any of a number of different functions, it always takes on an oscillatory form, hence we call it as wavelet. As I mentioned, the star indicates the operation of conjugation, complex conjugation, and we have 1 by square root A. It is a normalizing factor which ensures that the energy is the same for all values of A, all values of B as well, since translations do not alter the wavelet energy. Now if B is 0 and A is 1, then the wavelet is in its natural form. As I mentioned, we can call that as mother wavelet, that is pi 10t. Here 1 corresponds to A and 0 corresponds to B, that is equal to phi t, which is called as a mother wavelet. Now we'll see a mother wavelet in the figure along with some of its family members that are produced by dilation and contraction. So the figure in the next slide, I'll show that. It will show a mother wavelet, that means in that case A is equal to 1. Then we will see two dilations corresponding to the value of A equal to 2 and 4, and one contraction with the value of A less than 1, that is we are considering 0.5. So you can see here, so this is for A equal to 1, this value, so this will be a kind of mother wavelet, and we are considering this is a Morlet wavelet which we are considering here. So you can see it is defined as e raised to power minus t square cos pi square root 2 by natural log 2, and it is again dependent upon the time parameter. So we are seeing here, we can see like you just for this is a for a 0.5, a equal to 2, a equal to 4, and a equal to 1. So that corresponds to the mother wavelet, and then we have dilation and contraction. The wavelet coefficients WAB mainly describe the correlation between the waveform and the wavelet at various translations and scales, the similarity between the waveform and the wavelet at a given combination of scale and position AB. The coefficients provide the amplitude of a series of wavelets over a range of scales and translations that would need to be added together to reconstruct the original signal. Wavelet coefficients correspond to changes in the waveform, most strongly to changes on the same scale as the wavelet, and most strongly to changes that resemble the wavelet. Since the continuous wavelet transform decomposes the waveform into coefficients of two variables, that are A and B, a double summation or integration is required to recover the original signal from the coefficients, because now we have two variables A and B. So it will be given as xt is equal to 1 by c, and we have two integration, one is corresponding to a and b, other one is b, and both are running from minus infinity to plus infinity. WAB phi ABT DADB, that is with respect to a and b. Here c is basically admissibility condition, which is given as, you can see, integration minus infinity to plus infinity mod of phi omega square by mod omega, and it is integrating with respect to omega, and mainly c is lying in the range of 0 to infinity. Now, why we need wavelets for EEG signals? As we know that EEG signal is non-stationary in both time and space. So specific components in the EEG signal may be localized in time, space, and scale. So wavelet analysis provides flexible control over the resolution with which EEG components and events can be localized in time, space, and scale. Wavelets possess the ability to optimize the window size of its analyzing functions over the entire range of scales in EEG. Hence, both the large and small scale structures of EEG can be resolved. This information helps in choosing the accurate bands for the analysis of EEG. So you can see the steps which we use in denoising the EEG signal. So considering a noisy EEG signal, first we apply the wavelet transform. Then after recovering the wavelet coefficients, we are applying the threshold, and then these we can say the filtered signal coefficients are again converted back to a signal by using inverse wavelet transform to get a denoised EEG signal. So you can see this wavelet analysis. We have small scale coefficients, and this corresponds to small scale wavelet. So this is you say it is this compute we are computing the coefficient corresponding to this, and one by one we are translating. This is a ERP signal, and it is a large scale wavelet. So you can see the variation of a small scale wavelet and a large scale wavelet. And if we reconstruct the large scale coefficients, you can see how we are achieving the large scale coefficients. So this can be we can apply this algorithm like we have contaminated EEG signal, which is divided into two frames of 2-second epochs. Then we are applying wavelet transform and the coefficients for all the scales are obtained. Then what we mentioned, we have seen in the block diagram that we have to use a threshold value which is calculated for each scale. Now using this thresholding function, the noisy coefficients are shrink. Then what we are doing, we are applying the inverse wavelet transform. Now we have to check whether we have some more epochs or no. So if we have more epochs, again we will apply the wavelet transform and will compute the coefficients, and like this the method will go on. But if there are no more epochs, then we concatenate all the denoised epochs. Now what we mean by successive thresholding of wavelet coefficients. So many researchers have shown that mainly in for this we are considering this Tarjana Zikov et al. 2002 paper. The threshold limit was calculated from the baseline EEG, which is presumably artifact free. So the recording procedure to obtain such an artifact-free EEG calls for a cooperative patient and is not only tedious but also very rarely free from contaminations. So the proposed algorithm eliminates the need for calculating the threshold limit for the artifact-free EEG data. So we'll discuss the number of we are different steps in this. So what we are doing is in step 1, wavelet transform is used to decompose the recorded EEG signal, let's suppose Xn, which is contaminated by ocular artifacts that are mainly related to our eye variations. We have already seen these kind of artifacts present in the EEG signal and the wavelet coefficients. So these are the wavelet coefficients we are representing by capital U and J. So it is a vector at each scale J, where J is nothing but A to capital J we are obtaining. Then in step 2, we are thresholding these coefficients at each scale J based on the selected threshold limit by applying an appropriate thresholding function. So then the threshold wavelet coefficients, as we are representing by V cap Nj, it is again a vector, are the estimate of the coefficient values of X cap Tr n. Then the denoised reconstructed signal is obtained by applying the V inverse wavelet transform on the threshold wavelet coefficients, and we are representing them by capital V cap Nj. Now the previous steps are repeated successively for appropriate number of times, or we can say stages, with the reconstructed signal as input till the desired performance goal is achieved. Now what can be the choice of the wavelet transform and the decomposition level? So we can use stationary wavelet transform or we can also go for time invariant transform. It has better sampling rates in the lower frequency bands when compared to discrete wavelet transform. Mother wavelet, how we can choose the mother wavelet? So coif wavelet is chosen as the basis function since the shape of its mother wavelet resembles the shape of eye blink artifact, that is mainly for ocular artifacts. Now decomposition level, to have reasonable computational complexity, the decomposition level is taken to be 5. And how we are calculating the threshold limit? So it determines how thresholds are computed. It is researched in many of the papers. So we can have Donohoe's universal threshold. It is given as Tj equal to square root 2 sigma square natural log n, or we can use the method based on statistics of the signal given by Tarjana Zikov et al. It is mean Hj plus 2 into standard deviation capital Hj. Also, the thresholding function, it determines how thresholds are applied to the data. Now we'll see different results that are proposed and in the papers. So this figure shows the results for successive thresholding algorithm using Donohoe's threshold, and we are considering 10-second epo. You can see this is first stage it is showing, and it is the second stage. We are removing more epochs by using number of stages. Blue line in this, you see it is EEG with the artifact, and this red line, if you see, that is concatenated EEG signal. Again, we can see the results corresponding for 1 second EPO. These figures, if you see, it is representing the correlation coefficient between the EEG signal with the artifact and concatenated EEG signals. Again, we are considering this for 1 second, first stage and second stage. Now we have to note that the preservation of high frequency contents of the original signal is good in the wavelet based approach. The threshold values are calculated from the uncontaminated EEG itself, and the selection of an appropriate threshold limit and threshold function is context sensitive. We'll see another condition or the other area where we can use the wavelets. It is ocular artifact zone identification and removal of ocular artifact using wavelet transform. So we have in this ocular artifact zone identification algorithm. So in this, the step 1 is to have contaminated EEG, and then we decompose that by using HAR wavelet. Here we are using HAR as a mother wavelet up to 4 levels. So decomposition level we are using 4, and then we are reconstructing the wavelet coefficients. Also in this we are applying first order difference. We are calculating from this array, and mean of all the positive values and negative values are calculated, and then positive threshold, negative threshold and difference threshold values are empirically computed using the mean values. Now based on these three threshold values, the difference array is checked to identify the start and end time index values of the ocular artifact affected time zones. Then the stationary wavelet transform is applied with coef as the basis function to the contaminated EEG with ocular artifact zones identified. So for each identified ocular artifact zone, successive thresholding algorithms are applied to threshold the wavelet coefficients, and then inverse stationary wavelet transform is applied to the threshold wavelet coefficients to obtain the artifact-free EEG signal. So this diagram shows the different steps. We have contaminated EEG channel input, and then we have reconstructed signal from level 4 HAR wavelet decomposition of the contaminated EEG. Then we have computed the first order difference of the above reconstructed signal, and then we have marked the ocular artifact zones. It is worth noting here that reconstructed coefficients at level 4 results in a step function. You can see it results in a step function with a rising edge for a change in the state of eyes from open to close, and a step function with a falling edge. Now here you can see a sample of EEG with both eye blink and eye movement artifact with ocular artifact affected time zones. You can see here we have identified these ocular artifact zones. So again we have applied successive thresholding algorithm to the identified OA zone using Donohoe's threshold limit, and as by having, we can say, the coif wavelet. So you can see the blue one is again the EEG with artifact, and red one is the corrected signal which is concatenated different epochs, but here we are considering this, we can say, You can see 1 second EPO we are considering. So this was all in this lecture. For this, you can refer the book by Rangaraj M. Rangayan, Biomedical Signal Analysis, a Case Study Approach. So thank you so much.